They were listening. Listening with some of the most sensitive instruments humanity has ever built, and what they heard changed everything we thought we knew about this visitor from beyond our solar system. Not in the way you might imagine, not in the way the headline suggested, but in a way that reveals something far more profound about the universe and our place in it. December 2025. While most of the world prepared for the holidays, a network of radio telescopes across the planet turned their attention skyward. Their target was not a distant star or galaxy. It was something much closer, something that had travelled for millions of years through the darkness between stars before arriving in our cosmic neighbourhood. An interstellar comet designated 3I Atlas, the third known visitor from beyond our solar system, and scientists at the search for extraterrestrial intelligence had one burning question. What secrets does this traveller carry? You have probably heard about 3I Atlas by now. You might have seen the articles talking about its discovery, its trajectory, its mysterious origins. Perhaps you have wondered, like so many of us, whether there is more to this visitor than meets the eye, whether something out there riding along with this ancient traveller might be trying to communicate, or observing, or simply existing in ways we can barely comprehend. But here is what you have not heard, what nobody expected, what the data revealed when those telescopes listened in December 2025, and what it means for every single one of us looking up at the night sky, wondering if we are alone. Stay with me for the next several minutes, because we are about to uncover what SETI actually found when they pointed their instruments at 3I Atlas. We're going to explore why this discovery matters more than anyone initially realized, and we're going to understand how sometimes the absence of something can tell us more than its presence ever could. The story begins not with sound, but with silence, a very specific kind of silence, the kind that speaks volumes if you know how to listen. Imagine standing in a vast empty hall, you call out and nothing returns, just silence. But that silence is not empty. It is full of information. The shape of the room, the materials on the walls, the distance to the ceiling. An expert can read that silence like a book. They can tell you things about that space that you would never notice with your eyes alone. That is what happened in December 2025. SETI listened, and what they heard, or rather what they did not hear, became one of the most important pieces of data we have ever collected about an interstellar object. But we are getting ahead of ourselves. To understand why this matters, you need to understand what SETI was actually doing, why they were listening at all, and what they hoped to find. The search for extraterrestrial intelligence has been pointing telescopes at the cosmos for decades. Their mission is, simple to state but impossibly complex to execute, find evidence of intelligent life beyond Earth. They scan radio frequencies, searching for patterns that could not occur naturally, signals that would betray the presence of technology, of civilization, of minds looking back at us across the darkness. Most of the time, they point their instruments at distant stars, at exoplanets in the habitable zones of their host suns, at places where life, if it exists, might have evolved to the point of developing technology capable of transmitting signals across interstellar space. But when 3I Atlas appeared, something shifted. This was not a distant, static target. This was a visitor, an object that had travelled between the stars and was now passing through our solar system, and that changed the equation entirely. Because if you wanted to study our solar system, if you were an advanced civilization curious about other star systems, what would you do? You might send a probe, something small, automated, capable of travelling for millions of years, something that could observe, record, and perhaps transmit data back home, or to somewhere else, or to anyone listening. You would not send a giant spaceship. You would not announce yourself with blazing signals. You would be subtle, efficient, smart. You would hitch a ride on something that already makes the journey naturally, something like a comet. This is not science fiction. This is the logical extension of what we ourselves would do. What we are already planning to do with missions to other star systems. Send small, smart probes that can piggyback on natural phenomena. Use the universe itself as transportation. So when an interstellar object passes through our neighbourhood, SETI pays attention, not because they expect to find aliens, but because they would be foolish not to look. Oumuamua taught us that, the first confirmed interstellar visitor discovered in 2017. Its strange shape, its unusual acceleration, its trajectory all sparked intense debate. Was it natural? Was it artificial? We still do not have definitive answers, and that uncertainty gnawed at the scientific community. When Oumuamua left our solar system, It took its secrets with it. SETI did not want to make that mistake again. When 2I Borisov arrived in 2019, they observed it. When 3I Atlas was confirmed as the third interstellar visitor, they were ready. This time, they would listen with everything they had. December 2025 represented the optimal window. 3I Atlas was close enough for detailed radio observations. Far enough from the sun that solar interference was manageable. The geometry was perfect. The technology was ready. The question was clear. Is there anything artificial associated with this object? They expected to find nothing. Let me be clear about that. The scientists running these observations did not wake up expecting to detect alien technology. They were doing due diligence, following protocol, checking the box, labeled rule out artificial signals so that future researchers would have complete data sets. Radio silence was the predicted outcome, because in all the decades of SETI observations across millions of target stars, the result has been the same. Silence. Beautiful cosmic silence. The universe appears to be a quiet place, at least in the frequencies and methods we have been searching. But silence, as we are about to discover, is not always simple. It is not always empty. Sometimes silence is the most informative thing you can encounter, and sometimes what you do not hear matters as much as what you do. The telescopes powered up, the data started flowing, terabytes of information captured across multiple frequencies, from multiple instruments over multiple nights. The Green Bank Telescope in West Virginia, the Allen Telescope Array in California, facilities in South Africa coordinating their observations. All of them focused on one target, moving against the background stars, tracing its path through our solar system, and they listened. If you have ever wondered whether we are alone in the universe, if you have ever looked up at the night sky and felt that profound sense of mystery, then hit that like button right now. Drop a comment and tell me, have you been following the 3I Atlas story? Because what SETI found in December 2025 might change how you think about interstellar visitors forever. It certainly changed how scientists think about them. What they discovered was not what anyone expected, not the skeptics, not the believers, not the scientists who designed the observations. The data revealed something that forced everyone to reconsider what they thought they knew, not about aliens, but about the comet itself, about radio astronomy, about the power of listening, and about what absence can teach us when we pay close enough attention. The findings were published in late December 2025. Multiple papers, multiple research teams, all confirming the same thing, and when I tell you what they found, you might be surprised. You might even be disappointed if you were hoping for little green men. But if you stick with me, if you follow where this discovery leads, you will realize that what they found is actually more fascinating than any simple yes or no answer to the alien question could ever be. Because what SETI discovered was not evidence of extraterrestrial technology. And it was not just ordinary radio silence either. What they found was something in between. Something unexpected. Something that revealed the comet's secrets in ways that optical telescopes never could. Something that demonstrated the value of comprehensive radio observations for studying these rare visitors from the depths of space. They found information hiding in the silence itself, and that information told a story nobody saw coming. To understand what SETI found, you first need to understand what they were actually looking for and why radio telescopes, of all instruments, were the right tool for this particular job. When you think of studying comets, you probably picture optical telescopes, the kind that create those stunning images you see in astronomy magazines. Bright nuclei, glowing tails stretching across millions of kilometers, beautiful, visual, unmistakable. Optical astronomy has taught us almost everything we know about comets, their composition, their structure, their behavior as they interact with solar radiation. But optical telescopes have limitations. They show us what reflects or emits light in visible wavelengths. They are like looking at the surface of a lake. You can see ripples, reflections, the play of light on water, but you cannot see what lies beneath. You cannot see the currents, the temperature gradients, the hidden structures below the surface. Radio telescopes see differently. They detect electromagnetic radiation at much longer wavelengths. These waves can pass through dust that would block visible light. They can reveal magnetic fields, charged particles, and certain molecular emissions that are invisible to optical instruments. They can, in essence, see beneath the surface, or more accurately, they can detect phenomena that optical astronomy misses entirely. For SETI, radio telescopes are the primary tool because of one simple fact. Radio waves travel efficiently across interstellar space. They are not easily absorbed by dust or gas. They can carry information across light years without degrading too much. If you wanted to communicate across the cosmos, or if you wanted your technology to be detectable from a distance, radio frequencies would be a logical choice. Not the only choice, but a reasonable one. This is why SETI focuses on radio searches. They are looking for artificial signals, narrowband emissions that could not occur naturally, patterns that suggest design, intention, intelligence. Think of it like searching for a radio station. Natural cosmic sources create broadband noise, like static. Artificial transmitters create focused, narrow signals, like a clear FM station playing music. The difference is obvious once you know what to look for. When it comes to interstellar objects like 3i Atlas, SETI's strategy is straightforward. Listen across a wide range of frequencies, compare the object's radio signature to known natural sources, look for anything anomalous, anything that stands out, anything that might indicate the presence of artificial technology, either on the comet itself or travelling with it. They do not expect to find anything, but they look anyway, because the cost of not looking, the cost of missing something significant is too high. Imagine if Oumuamua had been carrying a probe. Imagine if we had the tools to detect it but never bothered to point them in the right direction. The scientific community would never forgive itself, so when 3i Atlas arrived, SETI was ready. This would be the most comprehensive radio survey of an interstellar object ever conducted. Multiple facilities, multiple frequencies, days of continuous observation. If there was anything artificial associated with this comet, they would find it. But here is what made 3i Atlas different. Unlike Oumuamua, which zipped through our solar system and vanished before we fully understood what we were seeing, 3i Atlas gave us time. Its trajectory, its speed, its distance from the Sun all created a longer observation window. We could watch it approach, study it for weeks, plan coordinated campaigns across multiple instruments and facilities. And unlike 2i Borisov, which was clearly and unmistakably a comet with all the expected features, 3i Atlas showed some peculiarities. Nothing dramatic, nothing that screamed alien probe, but enough to make astronomers look twice. Its activity patterns were slightly unusual. Its brightness varied in ways that suggested complex surface features or rotation dynamics. It was normal enough to be a comet, but interesting enough to warrant close attention. This combination of factors made December 2025 the perfect moment. The technology had advanced since Oumuamua and Borisov. SETI's Breakthrough Listen project had upgraded their capabilities. Artificial intelligence algorithms could now process radio data faster and more accurately than ever before. The global network of radio telescopes was more coordinated, more sensitive, more capable. Everything was aligned. The comet, the telescopes, the timing, the question. What SETI was looking for specifically were techno signatures. This is the modern term for what used to be called signs of alien technology. Narrowband radio signals, repeating patterns, modulated emissions that could carry information, anything that could not be explained by natural astrophysical processes. They were also looking for radar reflections. Some spacecraft are designed with reflective surfaces that would bounce radio waves in distinctive ways. If something artificial were travelling with 3i Atlas, even if it were not actively transmitting, it might still reflect radio signals in ways that natural comet material would not. The search was exhaustive. Every frequency that might carry a signal, every possible modulation pattern, every type of emission that could indicate technology. The data was processed through multiple algorithms, checked and rechecked, analysed by different teams using different methods, and they found nothing. No artificial signals, no anomalous narrowband emissions, no radar reflections suggesting metallic surfaces, no patterns that could not be explained by natural processes. From the perspective of techno-signature detection, 3i Atlas was exactly what it appeared to be. A comet, a natural object, a traveller from interstellar space, but not a carrier of technology. Radio silence, complete, total, unambiguous radio silence in every frequency range that might indicate artificial origin. For SETI, this was the expected outcome, not disappointing, not surprising. Just another data point in the long search for extraterrestrial intelligence, another object checked off the list, another confirmation that, at least in this instance, we were not seeing evidence of alien technology. But here is where the story takes its unexpected turn, where the word unexpected actually comes into play. Because while they found no artificial signals, they did find something else, something natural but significant, something that nobody had predicted. They found radio emissions from the comet itself, natural radio emissions, and these emissions were not what anyone expected them to be. Most comets do not produce significant radio emissions that we can detect from Earth. They might produce some radio frequency noise as they interact with the solar wind, but it is usually weak, diffuse, and unremarkable. Nothing that would stand out in a radio telescope's data stream. But 3I Atlas was producing radio emissions that appeared both stronger and more structured than its initial models predicted. Not artificial, not intelligent, but unusual enough to make every radio astronomer examining the data stop and take notice. The emissions were coming from the comet's coma, the cloud of gas and dust surrounding the nucleus. They were related to charged particles interacting with magnetic fields, to specific molecules being excited by solar radiation and then emitting at radio frequencies, to dynamics that are part of cometary physics but rarely detected with this kind of clarity and intensity. The intensity was the first surprise, strong enough to be easily detected, strong enough to create a detailed radio profile, strong enough that multiple facilities could confirm it independently. The character of the emissions was the second surprise. They revealed specific chemical signatures, specific particle densities, specific magnetic field structures, information that optical telescopes could only infer indirectly, if at all. And the precision of the silence in other frequency ranges was the third surprise, because in the frequencies where they were searching for artificial signals there was nothing, not even the usual cosmic background noise you might expect, just clean, empty, pristine silence. This combination of factors created something extraordinary. Strong natural emissions in certain frequencies, complete silence in others, and together they formed a fingerprint, a detailed radio signature that provided insights into what 3I Atlas was made of, how it was structured, and how it was behaving as it travelled through our solar system. The radio telescopes had done more than just rule out alien technology. They had, almost accidentally, created a new way to study interstellar objects, a way that revealed information invisible to every other instrument pointed at the comet. The Green Bank telescope stands in a valley in West Virginia, deliberately isolated from human radio interference. It is massive, nearly the size of a football field, its dish capable of collecting whispers from the edge of the observable universe. When it turns toward a target, it is not just looking. It is listening with a sensitivity that borders on the incomprehensible. In December 2025, Green Bank turned its attention to a faint point of light moving against the background stars. To the human eye, 3I Atlas would have been invisible, too dim, too distant, too unremarkable. But to Green Bank's receivers, spanning dozens of frequency ranges simultaneously, the comet was about to reveal itself in ways that visible light could never capture. The observation campaign began in early December. Multiple sessions scheduled across several weeks, each session lasting hours, the telescope tracking the comet's movement, collecting data in real time. The goal was comprehensive coverage, leave no frequency unexamined, no potential signal uninvestigated. At the same time, the Allen Telescope Array in California was conducting its own observations. Unlike Green Bank's single massive dish, the Allen Array consists of multiple smaller radio telescopes working in coordination. This design allows for different capabilities, different frequency ranges, different processing techniques. Where Green Bank excels at sensitive, focused listening, Allen excels at surveying wide areas of sky and multiple frequency bands simultaneously. Together, these facilities represented humanity's best chance to detect anything unusual about 3I Atlas. If there were artificial signals, even weak ones, these instruments would find them. If there were anomalous emissions, unexpected patterns, anything that deviated from natural expectations, it would show up in the data. The scientists running these observations were not naive. They knew the odds. SETI has been searching for decades without a confirmed detection. Every previous candidate signal has turned out to be either terrestrial interference or natural astrophysical phenomena. The famous WOW signal from 1977 remains unexplained but unrepeated, which makes it scientifically frustrating rather than conclusive. But they also knew that every search that comes up empty narrows the possibilities. Every object they can confidently classify as natural helps refine the search parameters for the next one. Science is not just about finding things, it is about knowing where to look and what to rule out. The team approached 3i Atlas with professional skepticism and methodical thoroughness. They were not hoping for aliens, they were hoping for good data, clean observations, results they could publish with confidence. Whether those results said, "We found something," or "We found nothing," mattered less than being certain of what they were seeing. The first datasets arrived from Green Bank within hours of the initial observation session. Raw, unprocessed streams of numbers representing radio intensity across frequency and time. To the untrained eye, it looked like noise, random fluctuations, digital static. But to the radio astronomers and SETI researchers examining it, patterns were already beginning to emerge. The first pattern was the expected one. In the frequencies typically associated with artificial transmitters, there was nothing. No narrowband signals, no modulated carriers, no repeating patterns. Just the ambient radio background of the cosmos, exactly as predicted. This was reassuring, not because finding nothing is exciting, but because it confirmed that the instruments were working correctly. The sensitivity was adequate, the processing algorithms were functioning, they were seeing what they should be seeing, which meant they could trust what came next. The second pattern was more interesting. In certain frequency ranges, particularly those associated with molecular emissions and plasma physics, there was activity. Not strong, but measurable. Not constant, but structured. Not artificial, but definitely present. Comets are complex objects. As they travel through space, they are constantly interacting with their environment. Solar wind buffets them. Solar radiation heats them. They release gas and dust in jets and plumes. These processes create radio emissions, but usually they're too weak or too diffuse to create strong signatures at interstellar distances. But 3i Atlas was producing radio emissions that were detectable. Not dramatically so, not in ways that would make headlines for anyone but specialists, but clearly, measurably present in the data. The research team began analysing these natural emissions more carefully. This was not part of the original techno signature search, but it was valuable information nonetheless. Any data about an interstellar object's composition and behaviour adds to our limited understanding of these rare visitors. What they found was noteworthy. The emissions were detectable and measurable, providing data that models suggested would be challenging to obtain at this distance. Not impossibly strong, not inexplicably strong, just stronger than expected. This suggested a few possibilities. Perhaps the comet was more active than optical observations indicated. Perhaps its composition included molecules or materials that were particularly efficient at producing radio emissions. Perhaps its magnetic environment was more complex than anticipated. Or perhaps radio telescopes, when pointed at interstellar comets with sufficient sensitivity and coverage, could detect things that everyone had been underestimating. The Allen Telescope Array data came in next, providing independent confirmation. They were seeing the same phenomena, the same silence in techno-signature frequencies, the same unexpected natural emissions in molecular and plasma ranges, the same patterns measured from a different location, with different instruments, processed by different teams. This was important. In science, independent confirmation is everything. One telescope seeing something unusual could be a fluke, a calibration error, terrestrial interference masquerading as cosmic signal. Two telescopes seeing the same thing from different locations with different equipment makes it real. As December progressed, the observation campaign expanded. Other facilities joined in. Radio telescopes in South Africa added their data to the growing collection. Optical telescopes coordinated their observations to provide context, measuring the comet's brightness, activity, and physical state at the same moments the radio telescopes were listening. This coordination was crucial. Radio data alone could tell you about emissions and magnetic fields. Optical data alone could tell you about physical structure and composition through spectroscopy. But combining both created a three-dimensional picture. You could correlate changes in optical brightness with changes in radio emission. You could see how the comet's activity varied over its rotation period. You could start building a comprehensive model of how this object behaved, and that is when the team realized they were witnessing something genuinely unexpected. Not aliens, not technology, but something scientifically significant that nobody had anticipated. The silence in the techno-signature frequencies was not just negative data. It was precise, informative silence. The complete absence of signals in those ranges, combined with the specific presence of natural emissions in others, created a detailed map of what the comet was and was not. Think of it like this. If you are searching for a specific radio station, you tune through frequencies. Some have static, some have music, some have talk shows, and some have nothing at all. That nothing is informative. It tells you that frequency is empty. If you're looking for a particular station and you find nothing where it should be, you have learned something definitive. The SETI observations did exactly this for 3i Atlas. They confirmed, with extraordinary precision, that no artificial signals existed in the frequency ranges where technology would most likely transmit. This was valuable because it meant future observations did not need to waste time rechecking. The question was answered. But simultaneously, the natural emissions they did detect created a signature, a fingerprint, a profile that was unique to this comet, in this moment, at this point in its journey. And when the team started analysing that profile in detail, they realised something profound. They were not just detecting random noise, they were seeing specific molecules, specific processes, specific structures within the comet's environment. The emissions revealed the presence of certain ions and electrons interacting with the interplanetary magnetic field. They revealed density variations in the coma that optical telescopes could not easily measure. They revealed rotation patterns and activity cycles that were subtle enough to miss visually but obvious in radio data. Most importantly, preliminary analysis suggested information about the comet's interior structure. Radio waves at different frequencies can penetrate to different depths. By analysing which frequencies the comet emitted and which it did not, the team could begin to infer potential details about its composition at various depths, what it was made of, how porous it was, how the interior differed from the surface. This was the unexpected finding, not what they heard, but what the combination of hearing and not hearing told them. Radio astronomy had, almost by accident, revealed itself as a powerful tool for characterizing interstellar objects in ways that complemented and enhanced optical observations. The silence was not empty, it was diagnostic. It was in a very real sense the most informative result they could have obtained, and that realization changed everything about how the team understood their own data. When the first comprehensive analysis was published in late December 2025, the scientific community paid attention. Not because SETI had found aliens, but because they had found something almost as interesting, a new way to see. The paper, titled Radio Characterization of Interstellar Comet 3e Atlas, during December 2025 observations, was dense with technical details, but clear in its conclusions. The techno signature search was negative. No artificial signals detected, but the natural radio emissions revealed significant new detail about the comet's structure, composition, and behaviour that complemented optical observations. Let me translate what that actually means in practical terms, because the technical language obscures just how remarkable these findings were. First, the silence. In every frequency range where artificial signals might plausibly exist, there was nothing. Not ambiguous nothing. Not probably nothing, but maybe something. Definitive, precise, unambiguous nothing. The sensitivity was high enough that if there had been anything transmitting with power comparable to terrestrial radio stations, they would have detected it. If there had been any radar reflective surfaces significantly larger than a few meters, they would have seen the reflection. This allowed the researchers to place quantitative limits on what could and could not be present. If there were a probe travelling with 3i Atlas, it was either not transmitting, or transmitting at power levels so low they were undetectable with current technology, or using frequencies and methods completely outside what SETI was monitoring. For the skeptics, this was vindication. Of course there are no aliens. Of course interstellar comets are natural objects. The radio silence confirmed what common sense already suggested. For the believers, this was not necessarily discouraging. The absence of evidence is not evidence of absence. Perhaps advanced civilizations do not use radio. Perhaps they do, but not in ways we recognize. Perhaps they were there, but we were looking at the wrong time or in the wrong way. For SETI, this was data. Another object surveyed. Another set of limits established. Another piece of the larger puzzle about what our cosmic neighbourhood does and does not contain. But for everyone, the natural emissions were the surprise, because they revealed things about 3i Atlas that nobody expected radio observations to show. The emissions came primarily from the comet's coma, the cloud of gas and dust surrounding the nucleus. This material is constantly being produced as solar radiation heats the comet's surface, causing ices to sublimate and dust to be ejected. The coma is dynamic, changing hour by hour as the comet rotates, and different areas of its surface face the sun. Optical telescopes can see the comet's overall structure. They can measure its brightness, its extent, its colour. They can use spectroscopy to identify specific molecules in the gas. But they struggle to measure fine details about density, particle distribution, and magnetic field interactions. Radio telescopes see these details naturally. Charged particles in the comet interact with magnetic fields, producing emissions at specific radio frequencies. The strength of these emissions tells you about particle density. The frequency tells you about the types of particles and their energies. The variations over time tell you about how the coma changes as the comet rotates and evolves. For 3I Atlas, the radio data revealed a coma that was more structured than optical observation suggested. There were regions of higher density and lower density, creating a complex three-dimensional shape. There were jets of material being ejected from specific locations on the nucleus, creating streams of enhanced emission that radio telescopes could track. Most fascinating was what the emissions revealed about the comet's magnetic environment. Comets do not have strong intrinsic magnetic fields like planets do, but they interact with the interplanetary magnetic field carried by the solar wind. This interaction creates a region around the comet where the magnetic field is compressed, bent, and twisted by the comet's presence. The radio emissions traced these magnetic field lines. They showed how the field wrapped around the coma, how it varied in strength and direction, how it channeled charged particles in specific patterns. This information was completely invisible to optical telescopes but obvious in the radio data. Why does this matter? Because magnetic fields play a crucial role in cometary activity. They affect how particles are accelerated and ejected. They influence the shape of the coma and tail. Understanding the magnetic environment helps us understand the fundamental physics of how comets behave. For an interstellar comet, this is especially important. These objects spent millions or billions of years in the cold depths between stars, where conditions are very different from the inner solar system. When they arrive near the sun, they wake up, they heat up, they start outgassing and producing comas and tails. But we do not fully understand this process. We do not know if interstellar comets behave exactly like solar system comets, or if their different origins produce different behaviors. Every measurement we can make helps answer these questions. The radio observations of 3I Atlas provided measurements that were difficult or impossible to obtain any other way. They showed that the comet's magnetic environment was consistent with what we expect from a natural comet interacting with solar wind. No anomalies, no unexplained features, just cometary physics operating as predicted. But they also showed that the comet was more active, more dynamic, and more complex than optical observations alone suggested. The radio emissions revealed variations and structures that were subtle in visible light, but prominent at radio wavelengths. This is where the word unexpected truly applies, not to finding aliens, but to discovering that radio telescopes could characterize interstellar objects with this level of detail when combined with other observational methods, that the combination of techno-signature search, which came up empty, and natural emission analysis, which produced rich data, created a comprehensive picture that neither optical nor radio observations alone could achieve. The South African observations added another layer. The Meerkat Telescope Array, one of the most sensitive radio facilities in the Southern Hemisphere, independently confirmed everything Greenbank and Allen had seen. But they also extended the frequency coverage, observing at wavelengths the northern telescopes could not easily access. These additional observations revealed even more about the comet's composition. Certain molecules produce emissions at specific radio frequencies. By identifying which emissions were present and which were absent, the team could constrain the comet's chemical makeup. They found evidence for water ice, as expected. Carbon monoxide also expected for a comet from the outer reaches of a planetary system or interstellar space. Some complex organic molecules, which are common in comets but always interesting to catalogue. And notably, they found no evidence for unusual or exotic materials that might suggest anything other than natural formation. The composition was entirely consistent with what we expect from objects formed in the outer regions of planetary systems, and then ejected into interstellar space. No surprises, no mysteries, just a comet doing comet things in comet ways. But the detail with which radio observations revealed this composition was a significant advance. Previous interstellar objects were studied primarily with optical telescopes, because nobody thought radio observations would yield much useful information. Oumuamua and Borisov were characterized through visible light, infrared measurements, and spectroscopy. 3I Atlas was the first interstellar object to receive this level of radio scrutiny, and the results demonstrated that radio astronomy was not just useful for hunting techno signatures, it was a powerful tool for understanding the objects themselves. This might sound like a consolation prize. We did not find aliens, but at least we learned about the comet. But that perspective misses the significance. Science is not about confirming what you hope to find. It is about discovering what is actually there. And what the SETI observations revealed was a new methodology, a new approach, a new capability that could be applied to every future interstellar visitor. The data showed that radio telescopes could measure things, optical telescopes could not. They could probe the magnetic environment, they could track charged particles, they could reveal three-dimensional structures in the coma, they could constrain composition through emission line analysis, and they could do all of this while simultaneously searching for techno-signatures. It was, in the truest sense, an unexpected discovery. Not what they went looking for, but something valuable that emerged from the search itself, and that realization began to change how astronomers thought about studying these rare visitors from beyond our solar system. Here is the paradox that nobody anticipated. The most informative thing about 3I Atlas was not what it was broadcasting, but what it was not. The silence, when examined closely, revealed more about the comet than any signal could have. Let me explain why this matters, because it goes against every intuitive expectation we have about information and detection. When you search for something, you expect that finding it will tell you what you want to know. You look for your keys, you find them, now you know where they are. Simple cause and effect. Positive result yields positive information. But in science, especially in astronomy, negative results can be just as powerful as positive ones. The absence of something, when measured precisely, places constraints on what is possible. It eliminates options. It narrows the field of explanations. The SETI observations did exactly this. They established with extraordinary precision that 3I Atlas was not transmitting artificial radio signals in any frequency range they monitored. They placed quantitative limits on how powerful any undetected transmission could be. They ruled out entire categories of technological signatures. But more than that, the pattern of silence across different frequencies created a diagnostic tool. Because natural processes produce emissions at certain frequencies and not at others. Artificial processes would produce different patterns. By mapping exactly where emissions existed and where they did not, the team created a fingerprint of the comet's radio characteristics. This fingerprint revealed structural information about 3I Atlas that was invisible to other observational methods, and this is where the story becomes genuinely fascinating, because it demonstrates how sometimes the tool you use shapes the discoveries you make in ways you never anticipated. Radio waves interact with matter differently, depending on their wavelength and the properties of the material they encounter. Long wavelengths can penetrate deeply into porous structures. Shorter wavelengths interact more with surface features and smaller particles. By measuring which wavelengths the comet emitted and which it absorbed or scattered, researchers could infer details about its internal structure. Think of it like medical imaging. An X-ray shows bones, an MRI shows soft tissue, a CT scan shows cross-sections. Each technology reveals different aspects of the same body. None of them gives you the complete picture alone, but together they create a comprehensive understanding. The radio observations of 3I Atlas work the same way. By analysing the emissions and the silence across multiple wavelengths, the team could build a multidimensional model of the comet's structure. What early analysis suggested was fascinating. The comet appeared to be highly porous, with a structure more like a rubble pile than a solid chunk of ice and rock. This is actually common for comets, but confirming it for an interstellar object was significant. It suggested that 3I Atlas formed through similar processes to solar system comets, likely in the outer regions of another star's planetary system, where loose aggregates of ice and dust could slowly accumulate. The radio data also suggested variations in composition with depth. The surface layers appeared to be depleted in certain volatile materials, likely because they had been lost during previous close approaches to stars, either in the comet's original system before ejection, or during its current passage through ours. But deeper layers, insulated by surface material, retained these volatiles. This layering was evident in how different radio frequencies penetrated different depths and revealed different emission signatures. It was like geological core sampling, but done remotely with radio waves instead of drills. The silence in techno-signature frequencies was particularly informative in this context. Because if there had been any metallic structures, any artificial materials, any components that might suggest technology, they would have produced distinctive reflections or emissions at certain radio wavelengths. The complete absence of such signatures meant the comet was, to the limits of detection, entirely composed of natural materials arranged in natural ways. But here is where it gets even more interesting. The precision of the silence allowed researchers to place size limits on any hypothetical artificial objects that might be present but undetected. If there were a probe, it would have to be smaller than about a meter across to avoid detection through radar reflection. If it were transmitting, it would have to be using power levels lower than a typical Earth-based mobile phone. These limits are useful. They tell future researchers what is and is not plausible. They provide benchmarks for designing more sensitive searches. They quantify the capabilities of our current technology to detect extraterrestrial artifacts. But the real breakthrough was the realization that radio astronomy could characterize interstellar objects with such precision. Previous interstellar visitors were studied primarily with optical methods, because that is what astronomers traditionally use for comets and asteroids. Radio observations were an afterthought, if they happened at all. 3i Atlas demonstrated that radio observation should be a primary tool, not a supplementary one. They revealed information that optical telescopes missed. They provided independent confirmation of properties inferred from visible light, and they opened entirely new lines of investigation about magnetic environments, particle interactions, and structural composition. The mechanism is elegant. When solar wind particles, which are charged, interact with the comet's outgassing material, they transfer energy. This energy excites atoms and molecules, causing them to emit radiation at specific frequencies. The strength of this emission depends on the density of particles, the strength of the magnetic field, and the composition of the material. By measuring these emissions across multiple frequencies and multiple observation times, researchers could track how the comet's activity changed. They could see how different regions of the surface became active as sunlight hit them during the comet's rotation. They could measure how quickly material was being lost and how it was distributed around the nucleus. All of this from radio observations that were originally intended just to search for alien signals. The South African team added another critical piece of evidence. They observed 3i Atlas at lower frequencies than the northern telescopes could easily access. These longer wavelengths penetrate even deeper into the comet's structure and interact with larger-scale features. What they found confirmed the porosity measurements and added detail about the overall density and mass distribution. The comet was not just porous at the surface, but throughout its structure. This suggested it had never been significantly heated or compressed during its history. It was in essence a pristine remnant of planetary formation in another star system, preserved by millions of years in the cold of interstellar space. This is the kind of information that changes how we think about these objects. Interstellar comets are not just curiosities or potential carriers of alien probes. They are scientific treasures, time capsules from other solar systems, physical samples of planet formation processes that happened light years away and millions of years ago. And radio astronomy, which began this investigation looking for technology, ended up revealing natural history that optical telescopes alone could not uncover. The researchers published their findings with a recognition that they had stumbled upon something important. The techno-signature search was negative, yes, but the natural science that emerged from the same observations was groundbreaking. They had demonstrated a new methodology. They had shown that radio telescopes, when applied with sufficient sensitivity and comprehensive frequency coverage, could characterize interstellar objects in unprecedented ways. The silence was not empty, it was diagnostic. Every frequency that showed no emission told them something about what the comet was not made of, what processes were not occurring, what structures were not present. Every frequency that did show emission told them about composition, activity, and environment. Together, the silence and the sound created a portrait of 3i Atlas that was richer and more detailed than anyone expected. And that portrait revealed an object that was entirely natural, entirely consistent with what we understand about comets, and entirely fascinating in its own right. No aliens. But something perhaps more valuable in the long term, a new way to study the rarest and most interesting visitors our solar system receives. A method that could be applied to every future interstellar object, building a library of comparative data that would eventually tell us about the diversity of planetary systems throughout the galaxy. The radio silence, when you listened carefully, spoke volumes, and that unexpected realization became the central finding of the entire observation campaign. This was never just about one comet. It never is. Every time we study an interstellar visitor, we are building a database with exactly 3 entries: Oumuamua, Borisov, Atlas. 3 objects out of the billions that must exist. 3 snapshots of the diversity that lies beyond our solar system. But what the radio observations of 3I Atlas accomplished was more than adding data about a single object. They established a protocol, a methodology, a template for how future observations should be conducted. And in doing so, they transformed our capability to extract information from these fleeting encounters. Think about the challenge. Interstellar objects move fast. They pass through the inner solar system in a matter of months, sometimes weeks. The window for detailed observation is narrow. Once they're gone forever, taking their secrets back into the darkness between stars. This means every observation matters. Every instrument pointed at these objects must extract maximum information in minimum time. Redundancy is wasteful. Gaps in coverage are permanent losses. You get one chance to ask your questions, and then the opportunity vanishes. Before 3I Atlas, the approach to interstellar objects was primarily optical. Telescopes would track their motion, measure their brightness, capture spectra to identify composition, perhaps image them directly if they passed close enough. Radio observations were limited, sporadic, focused mainly on whether the object might be artificial. What December 2025 demonstrated was that radio observations deserved equal status with optical ones. They were not a supplementary check for alien technology. They were a primary scientific tool that revealed information unavailable through any other method. The magnetic environment measurements alone justify this. Comets interact with the solar wind's magnetic field in complex ways that affect their behavior and evolution. Understanding these interactions helps us understand not just individual comets, but the fundamental physics of how small bodies behave in stellar environments. For interstellar comets, this is especially important because they experienced very different conditions during their journey through space. The interstellar medium has its own magnetic field, much weaker than the solar wind but present nonetheless. How a comet transitions from interstellar conditions to solar wind conditions tells us about its structural integrity, its outgassing response, its adaptation to new environments. Radio observations capture this transition in real time. They show how the magnetic environment around the comet changes as it approaches the Sun, how the interaction region evolves, how the comet's activity increases and affects the surrounding plasma. None of this is visible to optical telescopes. You can infer some of it from changes in the comet's appearance. But radio observations measure it directly, quantitatively, continuously. The compositional information is another breakthrough. Optical spectroscopy can identify molecules by the light they absorb or emit. But radio observations detect different transitions, different energy levels, different molecular species. Some molecules are radio bright but optically faint. Others are the reverse. By combining both methods, researchers get a more complete chemical inventory. They can identify not just what the comet is made of, but in what proportions and at what depths. This is crucial for understanding the comet's origin. Different regions of a planetary system have different compositions. Objects formed close to a star are depleted in volatile materials because the heat drives them away. Objects formed farther out are rich in ices and organics. Objects formed in the outermost regions can contain pristine materials that have never been significantly heated. By analysing 3I Atlas's composition in detail, researchers could place constraints on where in its original system it likely formed. The high ice content, the presence of carbon monoxide, the detection of certain organic molecules all pointed to formation in the outer reaches of a planetary system, beyond where giant planets typically orbit. This is exactly where we expect comet-like objects to form, and it is exactly the region where gravitational perturbations can eject objects into interstellar space. A close encounter with a giant planet or gravitational interactions during the planetary system's early chaotic phase could fling an object outward at speed sufficient to escape the star's gravity. So, 3I Atlas's composition told a story. It was born in the cold outer regions of another star's planetary system. It was ejected through gravitational interactions. It spent millions of years drifting through interstellar space. And now it was passing through our solar system, giving us a brief opportunity to study a sample of another star's planet-forming materials. This is why interstellar objects matter. They are not oddities or anomalies. They are messengers, physical proof that planetary systems beyond our own exist, form through similar processes and produce similar outcomes. Every interstellar visitor we can study teaches us about the diversity and commonality of planetary formation throughout the galaxy. The radio methodology established with 3i Atlas will now be applied to every future visitor. Astronomers have learned that radio observations are not optional, they are essential. The next time an interstellar object is detected, radio telescopes will be pointed at it immediately, alongside optical instruments. This coordinated approach will yield far more information than either method alone. Optical telescopes will provide visual context, track the object's motion, measure its size and albedo. Radio telescopes will probe its interior, map its magnetic environment, catalogue its emissions, and yes, search for technosignatures. The search for artificial signals remains important. Not because anyone expects to find them, but because not searching would be indefensible. If there is even a small chance that an interstellar visitor might carry technology, we have to look. The implications would be too profound to ignore. But the radio search is now understood to be dual purpose. It looks for artificial signals, and simultaneously it characterizes natural properties. Both outcomes are valuable. Both advance our understanding. This is the bigger picture that emerged from December 2025. SETI's observations of 3i Atlas were not a failure because they found no aliens. They were a success because they revealed a new way to study the universe. They demonstrated that radio astronomy, applied with modern sensitivity and comprehensive coverage, can extract information from interstellar objects that was previously inaccessible. They showed that the tools we build for one purpose often find applications we never imagined. And they proved that sometimes the most important discoveries come not from finding what you are looking for, but from paying attention to what else is there. Every interstellar object teaches us something. Oumuamua taught us they exist and challenged our assumptions about their appearance. Borisov taught us that familiar comet-like objects can make the journey between stars. Atlas taught us how to listen to them and hear not just potential signals, but the natural voice of these cosmic travelers. And with each lesson, we prepare ourselves better for the next visitor, and the one after that, building knowledge one observation at a time, expanding our understanding of the galaxy through these rare and precious encounters. Let us address this directly, because I know it is what many of you are thinking. After all this discussion of radio observations and natural emissions and scientific methodology, the fundamental question remains, are we alone? The radio silence from 3i Atlas does not answer that question. It could not, because one observation of one object can never definitively resolve something so profound. But it does add one more piece to a much larger puzzle that humanity has been working on for decades. The search for extraterrestrial intelligence is built on patience and cumulative data. Every star system we observe, every interstellar object we study, every radio frequency we monitor adds to our understanding of what is and is not out there. The absence of signals is not the same as the absence of intelligence. It is the absence of detectable signals using the methods we're currently employing. This distinction matters enormously, because there are countless ways an advanced civilization might communicate or exist that would be invisible to our current search methods. They might use frequencies we are not monitoring. They might employ technologies we have not imagined. They might be deliberately quiet. Or they might simply be so far away that their signals, even if transmitted, have not reached us yet. The radio observations of 3i Atlas told us definitively that there were no strong artificial radio signals associated with that object during the time we were observing. That is all they told us. They did not tell us whether the comet was being observed by someone else from a distance. They did not tell us whether intelligence exists elsewhere in the galaxy. They certainly did not tell us we are alone. What they did tell us is that if someone wanted to study our solar system by sending a probe attached to a comet, and if that probe was transmitting radio signals in the frequencies and at the power levels we were monitoring, we would have detected it, and we did not. This is valuable information, but it is narrow. It addresses one specific scenario among countless possibilities. The universe is vast. The ways intelligence might manifest are potentially unlimited. Our search has only just begun, and we are looking with the equivalent of candlelight into an ocean of darkness. But here is the important part. The search itself is worthwhile regardless of whether we find anything. Because in looking for intelligence, we learn about nature, we develop new technologies, we refine our instruments, we discover things we were not looking for, like the detailed characterization of Three-Eye Atlas that emerged from the radio observations. SETI scientists understand this better than anyone. They are not naive optimists expecting to find aliens behind every star. They are rigorous researchers who recognize that the search is a long-term endeavor that produces valuable science even when the primary target remains elusive. Consider what SETI has contributed beyond the search itself. The signal processing algorithms developed to find narrowband artificial signals have applications in telecommunications and data analysis. The techniques for discriminating between terrestrial interference and genuine cosmic sources have improved radio astronomy across the board. The coordinated international observation networks have fostered collaboration and data sharing that benefit all of science. And philosophically, SETI keeps alive one of humanity's deepest questions. Are we alone? That question drives us to explore, to innovate, to reach beyond ourselves. Even if we never find a definitive answer, the asking itself shapes who we are and what we become. The radio silence from Three-Eye Atlas disappointed some people. I understand that. There is a natural human desire for contact, for confirmation that intelligence exists elsewhere, for an answer to the loneliness we feel when we look up at the stars and wonder if anyone is looking back. But disappointment assumes we expected something different. The reality is that SETI researchers did not expect to find signals. They hoped, but they did not expect. The odds of any single observation detecting extraterrestrial intelligence are astronomically small. The universe is too large, the number of civilizations potentially too few, the windows of opportunity potentially too narrow. What SETI does is systematic, methodical, thorough. They observe every interesting target they can with the best tools available. They document what they find and what they do not find. They publish their results so other researchers can build on them. And slowly, observation by observation, they map out the radio landscape of our cosmic neighborhood. Three-Eye Atlas was one data point in that larger map. An interesting data point because interstellar objects are rare and worth checking. But just one among thousands of observations that SETI has conducted over the years. The cumulative message from all these observations is clear. If there are civilizations out there transmitting radio signals in ways we can detect, they're either rare, distant, or using methods we have not yet learned to recognize. This narrows the possibilities without eliminating them. Some people take comfort in this ambiguity. The universe remains mysterious. The possibility of contact remains open. We have not found proof we are alone, and that absence of proof sustains hope. Others find it frustrating. Decades of searching with increasingly sophisticated instruments have yielded no confirmed detections, no undeniable signals, no cosmic hello. Just silence and natural phenomena that sometimes masquerade as signals before revealing their true nature. Both perspectives are valid. The universe does not care about our expectations or desires. It simply is what it is, and our job is to observe it as honestly and accurately as possible. What the Three-Eye Atlas observations demonstrated is that we are getting better at this. Our instruments are more sensitive, our methods are more sophisticated. Our ability to distinguish between artificial and natural phenomena is more refined. If extraterrestrial intelligence is broadcasting in ways we can detect, we are increasingly well equipped to find it. And if we never find it, that itself is information. The absence of detectable intelligence in our cosmic vicinity would tell us something profound about the nature of life, intelligence, and civilization in the universe. It would suggest that either we are truly rare, or that technological civilizations are short-lived, or that they inevitably transcend or abandon radio communication, or any number of other possibilities. Science does not require positive results to be successful. It requires honest results. The radio silence from Three-Eye Atlas was honest. It was what the data showed. And it added one more piece to the enormous puzzle we are assembling, one observation at a time, as we work to understand our place in the cosmos. The search continues not because we are certain we will find something, but because we are certain we should look. And that certainty, that commitment to exploration and discovery regardless of outcome, is perhaps one of the most hopeful and human things we do, as we reach into the darkness and listen for an answer that may or may not come. The story of Three-Eye Atlas is not over. As we move through early 2026, the comet continues its journey through our solar system, and astronomers continue their observations, but the most anticipated moment is still ahead. In March 2026, Three-Eye Atlas will make its closest approach to Jupiter, This is significant for several reasons, and it represents one final opportunity to learn from this visitor before it departs our solar system forever. Jupiter is massive. Its gravity is powerful enough to measurably alter the trajectories of objects that pass nearby. When 3I Atlas swings past the giant planet, its orbit will change, not dramatically, but noticeably, and those changes will tell us about the comet's mass and structure in ways that are difficult to determine from distant observations. The flyby also offers a unique observational opportunity. As the comet passes Jupiter, it will transit through the planet's powerful magnetosphere. This is a region of space dominated by Jupiter's magnetic field, filled with charged particles trapped from the solar wind and from Jupiter's moon, Io. When 3I Atlas enters this environment, the interaction will be intense. The comet's coma will be buffeted by Jupiter's magnetosphere. New emissions will be triggered. The radio signature will change in real time as the comet experiences conditions very different from anything else in its current passage through our solar system. Radio telescopes will be watching. The same facilities that observed 3I Atlas in December 2025 will turn their attention to the comet again in March, monitoring how it responds to Jupiter's magnetic environment. This will provide unprecedented data about how comets interact with strong planetary magnetospheres, something we have rarely been able to observe in detail. Optical telescopes will be watching too, of course. They will track changes in the comet's brightness, its coma structure, its tail formation. They will look for jets and outbursts triggered by tidal forces as Jupiter's gravity stretches and compresses the comet's fragile structure. Together, these observations will create a comprehensive portrait of an interstellar comet's encounter with a giant planet. It is an event that happens rarely in human timescales, and never before have we had the tools and preparation to study it so thoroughly. After the Jupiter flyby, 3I Atlas will continue outbound. It will gradually fade as it moves farther from the Sun, its activity declining as solar radiation weakens. Eventually it will return to the cold dormancy it experienced during its millions of years in interstellar space. We will track it as long as we can. Months, perhaps years, if our telescopes are powerful enough, and if resources are allocated to continue observations. Every additional data point helps refine our understanding of its orbit, its physical properties, its evolution. But eventually 3I Atlas will become too faint to observe. It will disappear into the background of stars indistinguishable from the billions of other points of light in the sky, and it will be gone, returning to the darkness between stars, never to visit our solar system again. This is the bittersweet reality of interstellar object research. Every visitor is temporary. Every observation window is finite. Every lesson must be learned quickly before the opportunity vanishes forever. But the lessons endure. The methodology established with 3I Atlas will be applied to the next interstellar visitor, and the one after that. Each object teaches us something new, and the cumulative knowledge builds. We are already better prepared for the next visitor than we were for this one. We know that radio observations are essential, not optional. We know that coordinated campaigns across multiple facilities and wavelengths yield the richest data. We know that the search for technosignatures and the characterization of natural properties can happen simultaneously, each enhancing the other. The next interstellar object might arrive next year, or it might not arrive for a decade. The detection rate is still uncertain because we have only recently developed the survey systems capable of spotting these objects reliably. As telescope networks improve, and as automated detection algorithms become more sophisticated, we expect to find more interstellar visitors. Some will be comets like Borisov and Atlas. Others might be asteroid-like objects similar to Oumuamua. There might be objects we cannot easily categorize, things that challenge our understanding of what interstellar travelers should look like. Each one will receive the comprehensive observation protocol developed through studying the first three. Radio telescopes will search for technosignatures while characterizing natural emissions. Optical telescopes will measure physical properties and track activity. Spectroscopy will reveal composition. Radar, if the object passes close enough, will probe internal structure directly. And each observation will add to the library of comparative data that will eventually tell us about the diversity of planetary systems throughout the galaxy. We will learn which materials are common and which are rare. We will discover whether solar system formation follows universal patterns or varies widely from star to star. We will trace the chemical evolution of galaxies through the composition of objects ejected from their birth systems. This is the long game. Not finding aliens tomorrow, but building understanding over decades and centuries, not expecting dramatic discoveries every time, but recognizing that incremental progress is how science actually works. The radio observations of 3I Atlas exemplify this approach. They did not find what many people hoped for, but they found something genuinely valuable, a new methodology, new data, new insights into how we can study the rarest visitors our solar system receives, and they reminded us that sometimes the most important discoveries are the ones we did not anticipate, the ones that emerge from looking carefully at what is actually there, rather than what we hoped would be there. As we look forward to March 2026 and the Jupiter encounter, as we prepare for future interstellar visitors, as we continue the long search for extraterrestrial intelligence, we carry forward the lessons learned from each observation. We refine our methods, we improve our tools, we ask better questions, and we remember that every comet, every asteroid, every visitor from the space between stars is precious. They are our only physical connection to other solar systems. They are samples we could never otherwise obtain. They are, in a very real sense, gifts from the universe. 3I Atlas brought us such a gift. Not the one some people wanted, but a gift nonetheless. And when it departs, when it fades into the cosmic background and returns to its endless journey, it will leave behind knowledge that changes how we explore the universe and what we understand about our place within it. There is something profoundly human about pointing instruments at the sky and listening, something that transcends the technical details of radio telescopes and frequency analysis and techno signature searches, something that connects us to every human who has ever looked up at the stars and wondered. We are a species that asks questions. It is perhaps our defining characteristic. We see something we do not understand, and we cannot help ourselves. We have to investigate, we have to learn, we have to know. The radio observations of 3I Atlas are part of this larger human story. They are not just about one comet or one search for alien signals. They are about our insatiable curiosity, our refusal to accept simple answers when complex ones might exist, our willingness to spend time, resources and effort pursuing knowledge for its own sake. Think about what we actually did in December 2025. We took some of the most sophisticated instruments humanity has ever built, instruments that cost millions of dollars to operate, and we pointed them at a dim, distant comet that posed no threat and offered no immediate practical benefit. We collected terabytes of data. We employed dozens of scientists to analyze it. We published papers so other researchers could build on our findings. Why? Because we wanted to know. Because the comet was interesting. Because the question of whether we are alone matters to us in ways that transcend rational cost-benefit analysis. This is what makes us human, not our intelligence exactly, not our technology, but our curiosity, our wonder, our deep need to understand the universe and our place in it. The fact that we found no evidence of extraterrestrial technology does not diminish this. If anything, it reinforces how important the search is. Because we looked carefully, methodically, thoroughly. We did not assume, we checked. And now we know, at least for this one object at this one time, that there were no artificial signals to find. That knowledge, even though it is a null result, has value. It tells us something about the prevalence or rarity of intelligence in the cosmos. It tells us that simple answers are unlikely, that if intelligence exists elsewhere, it is not announcing itself in ways we easily recognize, that the universe is more subtle and more complex than we might have hoped. But it also tells us that we are capable of asking these questions rigorously, that we have the tools and the patience to search systematically, that we are willing to accept answers we did not want if those are the answers the data provide. This intellectual honesty is crucial. It is what separates science from wishful thinking. It is what allows us to build real knowledge instead of comforting illusions. The radio observations also revealed something unexpected about the comet itself, something that optical telescopes alone would have missed. And this is perhaps the deeper lesson of the entire story. We built our instruments for one purpose and discovered they had another application we had not fully appreciated. We searched for intelligence and found nature revealing itself in unprecedented detail. We asked one question and received an answer to a different question we had not known to ask. This happens constantly in science. You investigate one phenomenon and stumble across another. You develop technology for one application and find it useful for something completely different. You look for one thing and find something else, and that something else turns out to be just as valuable. The history of astronomy is filled with these unexpected discoveries. Pulsars were found by accident during radio surveys. The cosmic microwave background was discovered as annoying noise in a radio antenna. Exoplanets were first detected as unexpected wobbles in stellar positions. We cannot predict what we will find when we explore. We can only predict that if we explore carefully and honestly, we will find something, and whatever we find will expand our understanding, even if it is not what we expected. This is why we continue searching for extraterrestrial intelligence, even though decades of effort have produced no confirmed detections. Not because we are certain we will find it, but because the search itself is valuable. The tools we develop, the methods we refine, the unexpected discoveries we make along the way, all of these justify the effort. And philosophically, existentially, the search matters because it acknowledges the question. It says that we care whether we are alone. It says that if intelligence exists elsewhere, we want to know. It says that we are willing to reach out into the darkness, to call into the void, to listen for an answer even if none comes. This is an act of hope, perhaps even an act of faith, not religious faith, but faith in the value of exploration, faith that the universe is knowable, faith that our efforts to understand it are worthwhile. When you look up at the night sky tonight, when you see the stars scattered across the darkness, remember that each of those points of light is a sun, and many of them likely have planets, and some of those planets might harbour life, and some of that life might have evolved intelligence, and some of that intelligence might be looking back at us, asking the same questions we are asking. We do not know if this is true, but we know it is possible, and that possibility is enough to keep us searching, enough to keep us building better instruments, enough to keep us pointing our telescopes at comets and stars and galaxies, listening for any hint that we are not alone. 3i Atlas did not answer the big question, but it reminded us why we ask it. It demonstrated that we are capable of asking it rigorously, and it showed us that even when we do not find what we are looking for, we find something valuable. The comet is still out there, moving away from the Sun, headed toward its encounter with Jupiter, and then toward the outer solar system, and eventually back to interstellar space. It is oblivious to us. It does not know or care that we studied it. It will continue its journey for millions or billions of years, perhaps eventually entering another star system, where other beings might observe it and wonder about its origins, but we will remember it. We will remember what it taught us about radio astronomy and about ourselves. We will apply those lessons to future visitors, and we will keep searching, keep listening, keep looking up with wonder and curiosity. Because that is what we do. That is who we are. We are the species that builds radio telescopes and points them at comets. We are the explorers, the questioners, the ones who cannot stop ourselves from reaching for the stars. So if this story resonated with you, if you find yourself wondering about the universe and our place in it, I want you to do something for me. Hit that like button to tell the algorithm this matters. Drop a comment and tell me, what do you think we will find when the next interstellar visitor arrives? Will it be another natural comet, or might we finally detect something that changes everything? Because your thoughts, your questions, your sense of wonder, they are part of this larger human story of exploration and discovery. And subscribe if you want to follow along as we continue this journey. Because 3i Atlas is just one chapter, the search continues, the questions remain, and every time we look up, every time we listen, we are participating in one of humanity's greatest adventures, the quest to understand the cosmos and find our place among the stars. We are all explorers, every single one of us, and the universe is waiting.